Welcome to this explainer. All right, today we're pulling back the curtain on something we literally all use, but we rarely see for what it truly is. You know, when we type a prompt into an AI, it feels like this weightless magic happening somewhere way up in the cloud. But the reality? That cloud is made of massive, resource-heavy physical infrastructure right down here on the ground. And keeping that whole shebang running requires something far more tangible than data. It requires water, a lot of it.
So, let's dive right into this massive number off the bat. This represents the projected global water withdrawal of artificial intelligence. By the year 2027, which, let's be honest, is practically tomorrow, we are looking at 4.2 to 6.6 billion cubic meters. To put that completely astronomical figure into perspective, that is more than the total annual water withdrawal of 4 to 6 Denmarks combined, or about half of the United Kingdom. It's an incredibly vast amount of water being pulled from local sources, and it's happening largely under the radar.
Here's our roadmap for today. We're going to cover 1. AI's hidden water footprint, 2. How data centers drink water, 3. The cost of GPT-3, 4. The carbon-water conflict, and 5. Making AI sustainable. Let's get into it.
Starting off with Section 1, AI's hidden water footprint. Which brings us right into Section 2, how data centers drink water. We're all pretty used to hearing about the carbon footprint of our tech, right? But the water footprint, that is escalating rapidly. Major tech companies are withdrawing billions of liters of fresh water right now, primarily just to keep their massive computer systems from overheating. But there's a really critical distinction we need to make right away here. Withdrawal versus consumption. You're going to hear these terms a lot. Water withdrawal shows a data center's dependence on local resources, how much they're pulling out of the ground or local pipes. But water consumption? That means the water has evaporated. Think of withdrawal like borrowing a cup of sugar from your neighbor, but consumption is actually baking it into a cake. It's gone from the local environment forever. Both matter, for sure, but consumption directly impacts downstream water availability for the community.
This whole AI water footprint thing is comprehensively divided into 3 distinct scopes. Scope 1 is what happens on-site, evaporating water right inside the data center's own cooling towers. Scope 2 zooms out to the off-site power plants, because it takes water to generate the massive amounts of electricity these servers demand. And finally, Scope 3 goes all the way back to the manufacturing pipeline, where specialized, ultra-pure water is required, water so heavily filtered it's actually industrial grade, just to fabricate the physical servers and AI chips themselves.
Now let's really zero in on Scope 1, the on-site cooling. Here's the deal. Servers convert practically all of their electricity directly into heat. To get rid of that heat, data centers push it out to cooling towers, which dissipate it by evaporating water right into the atmosphere. Depending on the weather, they evaporate between 1 and 9 liters of water for every single kilowatt-hour of server energy used. And here is the real kicker. They aren't just using gray water. They actively require highly treated, potable drinking water to prevent bacterial growth and mineral clogs in their pipes.
Moving on to Section 3, the cost of GPT-3. Let's look at the real-world water cost of training and running a massive model like OpenAI's GPT-3. Just to train the model, utilizing average U.S. data centers, researchers estimate a staggering 5.4 million liters of water were consumed. For context, that's enough to fill over 2 Olympic-sized swimming pools, just evaporated into thin air for one training run. And to be clear, that figure encompasses both the on-site cooling evaporation inside the data center and the off-site water consumed by the power plants generating the electricity.
But what about once the model is trained and we all start using it? This is where it gets incredibly relatable on an individual level. Every single time you prompt an AI like ChatGPT for roughly 10 to 50 medium-length responses, the system practically drinks a standard 500 milliliter bottle of fresh water. Literally. Imagine just pouring out a fresh bottle of water all over your desk every time you have a quick brainstorming session with ChatGPT. It adds up remarkably fast.
And get this, where your AI request is processed matters immensely. Notice the data here comparing different locations. We have on-site WEU, which is water usage effectiveness, and off-site EWIF, or energy water intensity factor. If your request goes through Washington State, you only get about 10 prompt per bottle because they rely really heavily on hydroelectric power, which happens to have a massive water footprint. But route that exact same query to Ireland with its cooler climate and wind power, and you get up to 70 prompts for the exact same amount of water.
Which leads us to Section 4, the carbon-water conflict.
Seeing those grid differences, you might be thinking, well, we just need to use green, renewable energy to fix this. But actually, scratch that, it's not that simple.
Data centers face a literal conflict of the elements. It's what researchers call follow the sun versus unfollow the sun. If you want to optimize for a low-carbon footprint, you want to run your heaviest server loads during peak daylight hours when green solar energy is super abundant. But if you want to optimize for water, you absolutely must avoid those exact same hot hours, because hot outside air causes massive spikes in water evaporation inside the cooling towers. To save water, you actually want to run them at midnight instead.
This leads to a startling realization from the researchers. Water and carbon footprints are complementary. They're not substitutable. Minimizing one might directly increase the other. A perfectly green, zero-carbon energy grid could still inadvertently bleed local water reservoirs dry if we aren't paying attention to the water metrics.
Finally, Section 5, Making AI Sustainable.
So how do we actually solve this invisible price tag and ensure explosive AI growth doesn't make global freshwater scarcity worse? The researchers outline a really powerful path forward. First, we need strict transparency. We should be including water footprint metrics right on AI model cards, just like we do for carbon. Second, we need comprehensive reporting that includes that tricky Scope 2 off-site water from power plants. But the most actionable solution? Clever spatial temporal scheduling. This basically means dynamically scheduling heavy AI training runs during those water-efficient nighttime hours and routing our everyday user queries to data centers located in cooler, wetter climates. It's really about making the AI smart enough to know where and when it should be thinking.
Look, artificial intelligence is an absolutely incredible world-changing technology. There's no denying that. But as we continue to lean on the cloud for answers, we have to remember that the cloud is rooted right here in the Earth. We need to actively ensure we're treating our physical resources with the exact same careful optimization as our digital ones. So I'm going to leave you with this thought. Next time you ask an AI a question, ask yourself, is the answer worth the water? Thank you for joining me for this explainer, and keep learning.